Hi, guys. In this chapter, we're going to skip around a lot. So we're still in chapter 4, but now we're doing section 4-8, which is called complex numbers. In our first video today, we're going to focus on just radicals, which is another way of saying a square root. And then we'll get into complex numbers in the second video. But let's just start with what we're used to, which is square rooting a number. So today we're going to be simplifying radicals. And so we're going to take a square root of a non-perfect square, something that does not have a square root, and we're going to simplify it. Now, we're not just typing it into a calculator and getting a decimal answer. When I say simplify, I mean I want it to get to the smallest radical or square root as possible. To do that, our first step is going to be to take the number underneath the square root symbol and do a factor tree on it. A factor tree is when you take a number and split it into two numbers that would multiply to make the original number. So like 605, I know for sure that's divisible by 5. So I put a 5 over here, and then I divided it in my calculator because I don't know that off the top of my head, and I got 121 for the other number. And then when you're simplifying your radicals and you're doing your factor tree, like you want to keep going until you have nothing but prime numbers. So a prime number is a number that you can't split into like two different numbers. So like 5 is a prime number because the only numbers that multiply to make 5 are 5 and 1. And that's kind of silly to just keep doing that because like we already wrote the number 5. But 121 is not prime. I can split up 121 into 11 times 11. Now 11 is prime, and so at this point in time, I would stop. What you're going to do next is you're going to replace the number underneath the radical with a multiplication problem. And it's the prime factorization, right? The 5, the 11, and the 11. So instead of the square root of 605, I'm going to do the square root of 5 times 11 times 11. Now, I didn't actually change this problem because 5 times 11 times 11 is actually 605. Okay, so I'm just writing it in a different way. If you will, I am substituting the number 605 with its prime factorization. Now, this is a square root. Square is an exponent of 2. And so when simplifying radicals, what you're going to do is you're going to look for pairs of numbers, 2, since it's a square root. In this problem, I have a pair of 11s. If you can find a pair of numbers, circle them. One of the numbers gets to escape out of the radical. And the other number, it's going to just kind of disappear. It gets lost in the void. It's not there anymore. So one number escapes, the other one, poof, it's gone. And you can only do this if you find pairs of numbers. The 5, which does not have a pair, it's just the number 5, it just stays underneath the square root. And so my 11 has escaped to the outside. My second 11 is poof, gone. And my 5 stayed on the inside. And so the simplified version of the square root of 605 is 11 rad 5. Okay, so again, the key to these problems is finding pairs. One escapes, one disappears. Let's try another one. So here I have the square root of 140. Now, as far as doing the prime factorization tree, it doesn't matter what numbers you start with because you're going to end with all the same prime numbers when you're done. So 140, my first instinct is to go 10, so 10 and 14. Neither of those are prime, so I am going to break them down a little bit more. So 2 and 7 for 14 and 2 and 5 for 10. Now, when I'm taking my prime numbers and I'm rewriting them in the square root symbol, I like to put them in numerical order, smallest to biggest, mostly because that'll automatically put my pairs right next to each other. So when I'm rewriting this, I'm going to go 2, 2, 5, 7. So now it's pretty obvious I have a pair of 2s. I do not have a pair of 5s. I do not have a pair of 7s. From my pair of 2s, one of them escapes out of the radical, and the other one is poof, gone. Now my 7 and my 5, that are not a pair of numbers, they have to stay inside the radical, and I am going to actually multiply them back together. And so my final answer for this problem is 2 rad 35. My escaped 2 and my 5 times 7. If you have multiple numbers that escape out of the radical, then you would also multiply those together. So this is one big multiplication problem. So anything that ends up on the outside all gets multiplied together, and anything that's still on the inside all gets multiplied together. Let's take this one step further. Let's throw some variables in there. Now I'm going to show you two different ways to deal with variables. If you're a visual person, you can do the circling thing like we did on the first couple of problems. And then if you're not a visual person, or if you're more an algebraic person, then I'm going to show you a second method. Let's start with the first method though, because it's very similar to the methods that we were just doing. So I am going to factor tree my 72. If you can get a pair of numbers that are not prime numbers, that's fine. So I have a pair of 6s, and I'm going to go ahead and just stop there because I know that I'm looking for pairs for 2 of a kind. So it's not necessary to break those down into 2, 3, and 2, 3. If you want to, you can. If you broke it down into 2, 3, 2, 3, then you would end up with 2, 2, 2, 3, 3 for underneath your radical. So you can end up with that, or you can just do 2, 6, 6. Either way, you're going to have a pair of 6s, or you'll have a pair of 2s and a pair of 3s, which will multiply to make 6. Okay. Now, with the variables, you are going to write out, right, x to the third means that I have 3-letter x's. Y to the fourth means I have 4-letter y's. And z to the fifth means I have 5-letter z's. So again, if you are a visual person, it does help to like write everything out. And then you're essentially going to be doing what we did on the previous two problems. So you're looking for pairs, 2 of a kind. So I have a pair of 6s. 1 6 will escape. The other one goes poof, gone. I have 3 x's, which gives me 1 pair, and then there's a third x that's left over. It doesn't matter which one is the leftover one, but you should have one that's left over. From my pair, 1 escapes and 1 is poof, gone. For my y's, I have a pair of y's, and I have a second pair of y's. So from my y's, 2-letter y's will escape, and 2 have poof, disappeared. And we're going to do the same thing with the z's. So I have 2 z's, and I have another 2 z's. And then similar to the x's, I have this one leftover z. So anytime that you can circle something, 1 will get out. So I have a 6, an x, 2 y's, and 2 z's that have gotten out. And then anything that is not circled stays in. So the 2, the x, and the z, all of those will stay in. And my final answer is a 6x y squared z squared on the outside, and then square root of 2xz on the inside. Now, if you're not a visual person, you do not have to write out all of the letter x's and y's and z's. It's a lot of writing. I like it because I like circling. But if that's not your style, there is another way that you could deal with exponents when they're underneath a square root. And we kind of talked about this when we were talking about factoring. So when you're square rooting a variable with an exponent, essentially you're taking your exponent and you're dividing it by 2, because a square root is looking for an exponent of 2. And so the alternative way to dealing with variables with exponents is you could divide the exponent by 2, and then if it doesn't divide evenly, then the remainder from your division problem will remain inside the radical. So let's take a look at that method. So looking at my letter x, I'm going to do 3 divided by 2. 2 goes into 3 once with a remainder of 1. So that means that 1x gets out here, and 1x remains inside. Okay, 1 out, 1 remaining. Let's try the letter y. It was 4. So 4 divided by 2 is 2 with no remainder. That means that 2 y's got out and none remained inside. And that's exactly what we got, right? Y squared on the outside, and there are no more y's on the inside. And then let's finish it up with that z. So 5 divided by 2, 2 goes into 5 2 times with 1 left over. So again, for the z, 2 escape, 1 remains. 2 escape, 1 remains. So this is an alternative method that you could use whenever you have exponents. This concludes our first video for today. In our next video, we'll learn about imaginary numbers.